Welcome. Today we're going to be talking about the importance of the periodic table of elements. So we've been using the periodic table a little bit lately. We've been talking about things like how to read it. We know that each cell contains the elemental symbol, the atomic number, and the average atomic mass. But certainly there has to be more to it. Otherwise, it would just make more sense to have a list of elements instead of a periodic table. So first let's talk about the history of the periodic table. The periodic table, as we know it, was first designed by Dmitri Mendeleev in 1872. Now at this point, for a few years, chemists have been trying to make some sort of table arranging elements based on their atomic number and their shared physical and chemical properties. But Mendeleev's brilliance is that he thought, maybe there are elements we haven't discovered yet. So in his table, he left gaps for elements that should be predicted but just hadn't been observed yet. And it turns out he was right. And based on Mendeleev's work, we were eventually able to come up with the current periodic table of elements. So the current periodic table has 118 known elements and is divided into groups and periods. So groups, those are the columns, and periods are the rows of elements. Now you might be wondering, why is the periodic table shaped the way it is? When we normally think of a table, we think, okay, nice square or rectangle, same number of cells in each row and each column, but we don't have that here. We have 2 elements in the first row, 8 in the second row, 4th row, we go up to 18. Well, there's a reason why it's designed that way. And it has to do with electron orbitals. So thinking back to our talks on electron orbitals, we know there are 4 types of orbitals: s orbitals, p orbitals, d orbitals, and f orbitals. Now the periodic table is arranged based on how those orbitals are filled up. So up top we have the 1s that's filled up first, then 2s and 2p orbitals, 3s, 3p, then we get on the 4s and the d orbitals, and then we have the f orbitals. So we divide these sections, they're often called the S block, P block, D block, and F block elements. Now we're not going to talk a whole lot about the F block elements because for the purpose of this course, they're not very important. Now we can also separate elements into main group elements and the transition metals. So the main group elements, these are the S and P block elements. They're also called the representative group. That's because these elements are the most abundantly found in nature. A characteristic of these elements is that they have a single oxidation state. The transition metals, so these are the D block elements, a characteristic of them is that they have multiple oxidation states. So for instance, iron. Iron has a 2+ or a 3+ oxidation state, depending on what it's bonded to. We can further divide the periodic table into metals, nonmetals, and semimetals. So metals, these are all these elements in tan there. Right? So they're good conductors of electricity and heat. Right? They're often very shiny, very malleable. The nonmetals, these are in blue, so they're good insulators of electricity and heat. Now, semimetals, as the name would suggest, lie somewhere between metals and nonmetals. They're not good conductors of electricity and heat, but they're not good insulators either. And these are shown in green. All right, so we're not going to talk a whole lot about the semimetals, but we're going to focus mainly on metals and nonmetals. Now, knowing whether an element is a metal or a nonmetal tells us what kind of bonding will happen between 2 elements. So remember, we have 3 types of bonding: ionic bonding, covalent bonding, and metallic bonding. So ionic bonding, remember this is when electrons are donated between atoms, and these happen between metals and nonmetals. So for instance, sodium chloride, table salt. Sodium, that's a metal. Chlorine, nonmetal, so it forms an ionic bond. Covalent bonds, remember this is the sharing of electrons between atoms. They form between nonmetals. So For instance, carbon dioxide. Carbon, nonmetal. Oxygen, nonmetal. So they only form covalent bonds with each other. All right, and then we also have metallic bonds, which we're not going to talk about nearly as much, but as the name suggests, metallic bonds are between two metals. So for instance, metallic elements in their solid state, or their elemental state, I should say, right, they form metallic bonds. Or metal alloys like bronze, which is a mixture of copper and tin. Copper, metal, tin is also a metal, so that alloy forms metallic bonds. Now we can also use the periodic table to figure out valence electrons in an element. So remember, valence electrons, every element wants to have a full octet, so it wants to have 8 electrons in its outer shell. Well, we know how many electrons are in its shell in the elemental state based on its group number. So group 1, 1 valence electron, group 2, 2 valence electrons, 3 valence electrons, so forth and so on. By knowing the number of valence electrons, we know that in an ionic compound we can determine the charge then, and in a covalent compound we can determine the number of bonds that are going to be formed. So if we're trying to figure out ionic charge based on valence electrons, well, let's start off with group 1. Group 1 has 1 valence electron, so it wants to get to 8. So it can either gain 7 electrons, or it can just lose 1 electron. Either way will give it a full octet that's going to be happy. So is it going to be easier to gain 7 or lose 1? Well, it's going to be easier to just lose 1 electron. So if it loses 1 electron, it's going to form a +1 charge. So all the elements in group 1 form +1 ionic charges. Group 2, same thing. It's easier to lose 2 than gain 6, so it's going to form +2 ionic charges. If we look at the other end of the table, well, first thing you might notice, the noble gases, they have a 0 up there, 0 ionic charge. Well, the noble gases, they already have a full octet. Right? They already have 8 electrons, so they don't want to lose or gain any. So they're not going to form ionic bonds. They're not going to form covalent bonds for that matter. They're very unreactive. That's a main characteristic of the noble gases. If we look at group 7, so the halogens, fluorine, chlorine, bromine, and iodine, they have 7 valence electrons. So it's going to be easier to gain 1 electron than to lose all 7. So they form -1 ionic charges. And same thing, group 6, easier to gain 2 than lose 6, so they form -2 ionic charges. You might notice, though, group 4, we don't have an assignment for that. Why might that be? Well, let's think about it. Group 4, so it has 4 valence electrons. So it can either gain 4 electrons, or it can lose 4 electrons. Neither is particularly easy. That's a lot of electrons to lose or gain, which is why group 4 elements tend not to form ionic bonds. They mainly form covalent bonds. So when you guys move on to organic chemistry, remember organic chemistry is the study of organic compounds, so carbon-containing compounds, you're going to be focused on covalent bonding with carbon. We can also look at the atomic radii and how that relates to an element's position on the periodic table. So you can see, if we go down a group, we have increasing atomic radii, so the size of the atoms increasing. If we go across a period, we see it's decreasing going from left to right. Why might that be? Well, first let's think about going down a group. So you might be wondering, what are these little n = 1, n = 2, n = 3 designations? Well, that tells you what outer shell there is. So we know n = 1 is the first shell that's the outer shell, n = 2, the second shell is the outer shell. So remember, as we're adding on these electron shells, they're further and further away from the nucleus. So the atomic radii is going to have to increase to accommodate for that. So that makes sense then why the atomic radii increases going down a group. What about going across a period, though? So we know that our radii is decreasing. Well, let's think about it in terms of valence electrons. Well, we know we have increasing number of valence electrons going from left to right. So as we increase the number of valence electrons, the electrostatic force between the nucleus and the electrons is getting stronger. So the nucleus is pulling in those electrons more strongly and thus decreasing the atomic radii. So going left to right, atomic radii is going to decrease. Now, based on this knowledge of atomic radii now, we can look at something called electronegativity. So electronegativity is the ability of an atom to pull electrons towards it. And we see from this table, going left to right across a period, electronegativity increases. And going down a group, electronegativity decreases. So as we're going across a period, remember, we have more and more valence electrons, so our atomic radii is decreasing. So the force pulling electrons in is stronger. So the electronegativity increases. Then similarly, going down a group, well, our atomic radii is getting larger and larger. So the force holding those electrons in is getting weaker and weaker. So our electronegativity is decreasing. Along the same lines of electronegativity, we have a concept called electron affinity. So electron affinity is similar to electronegativity, but it has a more technical definition. It's the ability of an atom to gain an electron in the gaseous, gain one electron in the gaseous state to form an anion. So we see going across a period, electron affinity is decreasing. So the energy required is getting less and less, which makes sense. If our electronegativity is increasing, it pulls electrons in more, so it's going to be easier to pull in an electron and form a cation. Going down a group, same principle. We see electron affinity is increasing. All right, our electronegativity is decreasing, so it's not pulling in electrons as easily, so the energy required to pull an electron has to increase. Similar to electron affinity, we have something called ionization energy, which is basically the opposite of it. Ionization energy, that's the energy required to lose an electron and form a cation. So, if we go across a period, we know electronegativity is increasing, so we know it's pulling in electrons more, so the energy required to rip one of those electrons away has to increase, and that's exactly what we see. If we go down a group, we see electronegativity is decreasing, so it's not holding in those electrons as easily, which means the energy required to take one of them away is going to decrease. Now you might notice there are a few exceptions. Now we're not going to talk about those right now, but when we move forward, we'll go into more detail. They relate to the orbitals and how electrons fill each s and p orbital. All right, so right now we've looked at some of the trends of the periodic table. Next time, we'll be talking about how we can use those trends to determine what types of bonds will be formed between different elements and the strength of those bonds, things like polarity